Welcome to our virtual presentation for 2013 Conference on the Constructed Environment. I am Izaskun Gallo, architect and PhD student at Universidad Politécnica de Madrid. I'm giving this presentation on behalf of Dr. Justo García Navarro and Dr. Trinidad Fernández Pérez. Here is our proposal: the influence of openings on energy demand of buildings, analysis of their characteristic parameters using LEADER software, Spain. This research will be published in the next issue of the International Journal of the Constructed Environment. First, I will introduce the subject of study, then explain the modeling of the opening and the studied parameters, and finally, describe and discuss the results, concluding with a brief summary of implications and applications. For the year 2020, each country of the European Union has set itself the goal of reducing CO2 emissions by 20%, improving energy efficiency by 20%, and increasing use of renewable energy by 20%. According to Yáñez, bioclimatic, solar or passive architecture offers environmental conditioning techniques for both heating and cooling that might save about 50% in energy consumption in buildings. In fact, to achieve these figures in renovation is very complex due to town planning concerns, regulation restrictions, economic and functional demands, and quantification difficulties. However, the International Energy Agency carried out research analyzing 14 pilot projects in cities in Central Europe. This research indicates that adopting solar efficiency techniques is cost and effort effective from financial, technical, and architectural viewpoints. These drawings show that the opening is a common element in the three types of basic solar heating systems: direct gain, indirect gain, and conservatory. In southern European countries such as Portugal or Spain, where winters are often mild and summers very hot, the opening can decrease energy consumption for heating and cooling by means of variations in architectural design of new and, importantly, existing buildings. The different functions that openings perform, ventilation, solar protection, daylighting, etc., turn them into control systems of the outdoor conditions. They can be designed as a system composed of a set of elements with specialized functions, that of the window unit and its bioclimatic potential. These windows from Greece and southern France show some low-technology alternatives in use for many years. Nowadays, the problem we are coming across when trying to apply traditional techniques that work well is the quantification of their energy savings. We, European Mediterranean countries, should revisit and reinstate these valuable techniques in new ways, using present techno-scientific knowledge wisely to consider all three economic, social, and environmental criteria of sustainability. This research aims to value the contribution to the energy balance of a space that depends on the main parameters of openings. We analyzed a generic cubic space with one opening with different configurations in Madrid. First, we calculated the energy demand in heating and cooling for the different configurations, then compare the respective outputs, and finally obtain the variation percentages of the demand, associating them with the parameters under evaluation. With this analysis, we can compare the contribution of each parameter to the energy performance of a building. LEADER is the software used to calculate the energy demand. LEADER software is used in Spanish building regulation to verify energy demand requirements according to the energy savings core document. LEADER is a free computer program that uses a dynamic and multi-zone simulation model to calculate heating and cooling needs of buildings. It calculates the thermal performance of a building per hour in transient state. It considers both external and internal conditions and also the effects of thermal mass. This program allows modifying the values of different characteristic parameters of openings, so it can be used to assess how much those parameters favor or damage the global energy demand of a building. These 14 parameters of the opening that you can see here were changed according to different combinations to a maximum of 430 different cases. As you see, these parameters were classified in two groups divided in different categories. The first group, marked in green, gathered those categories related to intrinsic architectural and constructive properties. The second group, marked in purple, puts together those parameters related to architectonic and constructive elements of indoor environmental control. LEADER compares the building under study with a reference building generated by the program which meets the minimum Spanish regulation requirements. Then it compares both of them, giving results in terms of percentages of heating and cooling demand with respect to the reference building. Obtained percentages from each set of cases were compared for every orientation, calculating the difference between upper and lower values. Thus, an estimation of the degree of variation achieved modifying the parameters in the study is obtained. Now, let us focus on the dimensions category. With different values of window-to-wall ratio and frame percentage, the generic space achieved maximum values of 18% variation in heating demand and 149% in cooling. Meanwhile, the minimum values of variation were of 7% in heating and 64% in cooling. The best results for cooling demand were in west orientation. The generic space with a window-to-wall ratio of 0 to 20% and 40% of frame fraction shows a reduction with respect to the reference building of 69% of the cooling demand. And that same space with a window-to-wall ratio bigger than 60% and 10% of frame fraction shows an increase of 218% with respect to the reference building. That means that there is a potential of variation in cooling energy demand up to 149% depending on the chosen window-to-wall ratio and frame percentage. Let's see now the results of the direct solar radiation category. By changing values of orientation, frame color or G value, we achieve maximum values of 15% variation in heating demand and 46% in cooling. Meanwhile, the minimum values of variation were of 5% in heating and 23% in cooling. Heating demand was higher in the generic space with the window facing north. Then, in order from the highest to the lowest value, east, south, southeast, west, and southwest, whereas cooling demand was higher in southwest, then, in order from the highest to the lowest value, west, southeast, south, east, and north, just the opposite. The most relevant results in this category were in north orientation. Even being north the coldest orientation, there is a potential variation in cooling demand of 23%. The generic space shows a reduction from the reference building of 65% of the cooling demand if a lightweight frame and 0.61 glazing G value are used, and a reduction of 88% from the reference building if a dark blue frame and 0.83 glazing G value are used. Have a look here at the materials category. With different values of frame and glazing U value and glazing G value, the generic space achieved maximum values of 15% variation in heating demand and 43% in cooling. Meanwhile, the minimum values of variation were of 5% in heating and 21% in cooling. The contradictions between advantages and disadvantages of using a standard or low E glazing are clearly shown in this case. In south orientation, heating energy demand is lower if standard glazing is used, with a potential variation of 15%. Meanwhile, in the same orientation, cooling energy demand is lower using low E glazing, with a potential variation of 35%. This example shows the conflicting requirements that openings must tackle in European Mediterranean countries, where winters are cold enough to require using solar energy for space heating, whereas summer conditions require maximum protection against solar radiation. In this research line, the shading elements offer great potential to address this problem, as shown in the next slides. This research studies 7 different types of shading elements: horizontal and vertical overhangs, returns, horizontal and vertical louver blinds, and 2 types of awnings. Parameters such as length of overhang, distance from the opening, depth of the return, depth of slats, distance between slats, and the inclination angle of slats or awnings were changed. Maximum values of 63% variation in heating demand and 85% in cooling were achieved, in both cases for horizontal louver blinds. Meanwhile, the minimum values of variation were of 5% in heating demand and 11% in cooling demand, both for returns. In all cases, the greatest potential for energy savings is in cooling energy demand. In order of priority, horizontal louver blinds show the best results of all the shading elements, with 85% maximum variation of cooling demand. That is the difference between using no blinds or louver blinds with 60 degrees slat inclination angle, depth 5 cm and distance between slats of 3 cm. Awnings are in second place, showing 63% maximum variation of cooling demand. As shown in this figure, the best result is for the awning with an inclination angle of 30 degrees. Then overhangs are in third place. They show 47% maximum variation of cooling demand. As shown in this figure, the best value is for an overhang of 2.50 meters long at 20 centimeters distance from the top of the opening. And in fourth place, returns. They show 16% maximum variation of cooling demand for a return of 1.35 meters depth. Finally, as regards the ventilation category, different values of air permeability, infiltrations, and air change rate were considered. These cases show the least potential for energy savings. Maximum values of 11% variation in heating demand and 2% in cooling were achieved. Meanwhile, the minimum values of variation were of 4% in heating and 0% in cooling. These results are useful when setting up priorities in decision-making processes that affect the design of the openings in a building, both for new buildings as for renovation. According to these findings, the greatest potential for energy savings through openings is in cooling demand. The priority order is as follows: first dimension, second shading elements, third solar radiation performance, fourth materials, and fifth ventilation. The potential for energy savings in heating demand is less but also significant. In this case, the order of priority varies slightly: first shading elements, second dimensions, third solar radiation performance, fourth materials, and fifth ventilation. In solar radiation performance and material categories, the fluctuation is very similar. What would happen if we combined all these energy savings potentials of openings using both aesthetic and dynamic elements to improve the thermal performance of our buildings? In Southern European countries, new buildings and refurbishment regulations should allow projects to explore the potential of openings in energy demand reduction, especially dimensions and shading elements, which are less explored than solar radiation performance, materials, or ventilation categories. It is essential to consider every orientation and its bioclimatic potential independently. The conclusions of this analysis are more relevant in qualitative than in quantitative terms, because numerical results might vary in different case studies. It is also necessary to consider that the onset hypotheses that have been used, as well as the hypothesis of leader software together with its default values, might influence the results. This article will be published in the next issue of the International Journal of the Constructed Environment. Amongst the references included, here are some of the most relevant used in the research. Thank you very much for your attention.